This is a quick video lesson on impulse and momentum. When you think about Newton's second law, if you are like most physics students, you think of it as force equals mass times acceleration. But Newton actually thought about it in a different way. Let's think about what acceleration really is. Acceleration is a change in velocity, delta v, over a certain time interval, delta t. And so force can be written as mass times the change in velocity divided by the change in time. Now this is really how Newton thought about it, but mass times velocity is a special thing. Mass times velocity is a quantity known as momentum. And so mass times a change in velocity is actually a change in momentum, delta p. P stands for momentum. So now we can rewrite Newton's second law to say that force is actually equal to a change in momentum, delta p, over delta t. Let's talk some more about what momentum is. So momentum is equal to velocity times mass. And the way we write this out, the symbol for momentum is p. So p equals mv. I've reversed them there, mass times velocity. It's really important to realize that momentum is different from velocity, and momentum is different from mass. So here are a couple of examples to think about. The top speed of a honeybee is almost exactly the same as a top speed of these football players when they hit each other after the ball is snapped. Even though their speed is the same, and their velocity could be the same, since their mass is very different, their momentum is very different. Momentum typically plays the biggest role in physics problems about collisions. So think about this collision. A honeybee hitting you will feel very different from one of these big football players hitting you. Let's think about a different example. If you think about a BB thrown at you compared with a BB shot at you, say out of a gun, that collision is going to feel very different. Their mass is the same, identical objects, but the speed with which it hits you is very different, and so their momentum is very different. Alright, I've given you some examples of things where the momentum was not equal, even though the velocity was equal or the mass was equal. Now let's look at an example where we're going to make the momentum equal. So this semi-truck up here, when it's fully loaded, it has a mass of somewhere in the neighborhood of 40,000 kilograms. This pickup truck down here has a mass somewhere in the neighborhood of 2,000 kilograms. Now, if this big rig has a velocity of just 2 miles per hour, it's only just getting going, 2 miles per hour. What velocity does this truck need to have the same momentum? Well, the momentum of the big rig, we're going to multiply its mass times its velocity, and we're mixing units in kind of a strange way. I recognize that, but this is still going to work in our example. This is going to be 80,000 kilogram miles per hour. Well, the mass of the truck down here is 2,000 kilograms, so we need a momentum of 80,000, and that's going to be equal to 2,000 times its velocity. So that means the velocity here needs to be 40 miles per hour. So in order for these two vehicles to have the same momentum, if the fully loaded truck is going 2 miles per hour, this pickup truck would need to be going 40 miles per hour. That's pretty impressive. Okay, let's go back to where I started with Newton's second law. So the way we're going to start thinking about it is force is equal to a change in momentum divided by a time interval. And then just to introduce you to the concept of momentum, I went through a few examples. Well, I'm going to do another algebraic rearrangement. So I'm going to multiply both sides by the delta t. So force times a time is equal to the change in momentum. Now, one important note here is that we got this equation by making an assumption. We got it from using acceleration equals delta v over delta t, but this is average acceleration. And so going back to my equation, what I'm really finding here is that the average force multiplied by a time interval produces a change in momentum. Now this is something I can use. So what I've discovered now is that if I know the average force acting on an object and how long that force acts, then I can tell you how much the momentum changes. Now, in most of the problems that we'll be doing, change in momentum can always be written as P final minus P initial, and this is equal to the average force times delta T. But in most of our problems, mass times V final minus mass times V initial, the masses don't change. The masses stay constant. And so I can almost always write this as force average times delta T equals mass. I'm going to factor it out. Times V final minus V initial. Do you know what? This is a kinematics equation. You've seen it before. If we divide both sides by m, here's what we get. We get the average acceleration times time equals the change in velocity, which is a kinematics equation that we worked with before. So what's new and different about this? Mostly what's new and different is some terminology. We've got momentum, and we actually have a special name for the average force times the time. This is called impulse. And the symbol for it is a capital J. And so what we have here is J equals delta P. This is the impulse momentum theorem. And we'll use it mostly to analyze impact events. So this is a really cool photograph of what a golf ball actually looks like as it's being struck with the golf club. As you can see, it deforms a lot, and this happens to most objects, even objects that we think of as being very solid and very difficult to bend. So the force of the golf club on the golf ball actually has kind of an interesting profile. As the golf club first makes contact with the ball, the force begins. It goes from 0 and starts increasing. As the ball deforms, the force increases until the ball reaches sort of a maximum deformation. Then the ball starts expanding outward and begins to prepare to leave the golf club. So the force decreases to the point where the golf ball leaves the golf club, and then the golf club has no more force on the ball. So this curve is actually kind of a complicated shape, and the area under this curve is equal to the impulse. So this is the area under the F versus time, force versus time curve. Calculating that area is very complicated because you have to understand the mathematics of this shape. Instead, we are going to take kind of a more basic approach, and we are going to calculate the average force which is going to lie somewhere around here. So this is going to be FAV. And the area under this curve is going to be exactly equal to a rectangle that takes place for the same amount of time, but at that reduced force that represents the average force. And so J is also the area of the rectangle. And the way we calculate this rectangle is average force times delta T, where delta T is here, the amount of time that this takes place. Well, this is just what we calculated in our impulse momentum. This tells us J equals delta P. Remember what those stand for? Impulse equals change in momentum. Let's review what we know about impulse momentum. The way we write impulse momentum is that J, which stands for impulse, is equal to delta P, which stands for change in momentum. We can expand this a little bit. J can also be written as the average force times the time that the force acts. This is impulse. And then the change in momentum can also be written as mass times the final velocity minus mass times the initial velocity. Both sides of the equation are vectors. Direction is important. This equation relates force, time, mass, and change in velocity. These problems that deal with impulse momentum are typically impact type problems, although any problem where you can calculate an average force and the amount of time that it acts will let you calculate the change in momentum.